The scheduler is a component of the operating system responsible for deciding which process runs on the CPU and when. It aims to provide acceptable response times for all users while maximizing the amount of time the CPU is performing useful work. An effective scheduling algorithm should also ensure fairness so that no single process dominates the processor. A ready queue is used to organize processes waiting to use the CPU. As processes arrive, complete, or are paused, they are added to or removed from the queue, ensuring tasks are handled in an orderly and efficient way. The first come, first served algorithm processes tasks in the order they arrive, like a queue. Each job is given equal priority, and the first job to arrive at the processor is the first one to be executed. The CPU continues running each process until it is complete before moving on to the next. An advantage of this scheduling algorithm is that it is simple to implement and requires minimal overhead, making it efficient to manage. In computing, overhead refers to the extra time, memory, or processing power required to manage a task or process, rather than doing the actual work itself. For example, in CPU scheduling, low overhead means the algorithm doesn't waste much processing time deciding which task to run next. Generally, the less overhead, the more efficiently the system can perform useful work. It also ensures fairness, as processes are handled in the exact order they arrive, and no process is skipped or starved of CPU time. A disadvantage is that it can lead to long waiting times if a large job arrives before shorter ones and offers poor responsiveness for interactive users. The round-robin algorithm gives each process an equal share of CPU time in turn, using a fixed time interval called a time slice. When a process's time slice ends, it is paused and placed at the back of a ready queue, allowing the next process to run. Round-robin allows users to receive quick responses, ensures the system can handle tasks or interrupts promptly, and enables multitasking. Round-robin ensures fairness by giving each process an equal share of CPU time and preventing starvation. Starvation refers to when a process is continually overlooked by the scheduler and never gets CPU time because other processes keep being prioritized. It also provides good responsiveness, making it ideal for time sharing and multi-user systems. However, its efficiency depends on the time slice length. Too short and frequent switching increases overhead. Too long and system responsiveness decreases, and processes may experience longer waiting times. With shortest job first, the operating system looks at all the processes waiting in the ready queue and selects the one with the shortest total execution time. Once a process starts running, it continues until it finishes. This is called non-preemptive. New processes that arrive must wait until the CPU is free, even if they are shorter. This approach reduces average waiting time but can cause starvation for longer jobs. With shortest time remaining, the operating system always runs the process with the least remaining time left to complete. If a new process arrives with a shorter remaining time than the current one, the CPU switches immediately to that new process, and that is called being preemptive. That is the main difference between shortest job first and shortest time remaining. This algorithm keeps the system responsive and ensures shorter tasks are completed quickly, but it can create high overhead and frequent task switching. A multi-level feedback queue uses multiple queues with different priority levels. Processes are moved between queues based on their behavior and how much CPU time they use. New processes usually start in the highest priority queue, and if a process uses too much CPU time without finishing, it is moved down to a lower priority queue, while shorter or interactive tasks remain in higher priority queues for faster responses. A multi-level feedback queue is flexible and adaptive, adjusting process priorities based on behavior and CPU use. It provides good responsiveness for short, interactive tasks while still allowing longer jobs to progress. However, it can be complex to configure and manage, as performance depends on how queues and time slices are set up. Lower priority processes may suffer starvation if higher priority queues dominate CPU time.